So we're going to do some examples of the substitution rule, and we're going to use the steps from the last video. So step 1 was to identify like our inner and outer function and kind of find the derivative of the inner function on the outside. So let's look at the exponential function we have here. We can consider that our outer function, and we have a 1 minus x squared on the inside. That looks like a pretty good inner function, and the derivative of 1 minus x squared is of 1 minus x squared is negative 2x. Now we do have an x here, which is just a constant multiple of the actual derivative of the inner function, which will be taken care of in one of our steps. As long as it's a constant multiple of our inner function, we're good. So we identified our inner function and our outer function. So next step is to write u of x equal to 1 minus x squared. We find our du dx is negative 2x. We can solve for dx, which would be dx equals du divided by negative 2x. And now we substitute these values in. So the integral of x e to the 1 minus x squared dx is equal to x times e to the u. And for dx, we're going to substitute in du divided by negative 2x. These x's will cancel. We can pull out this negative 1/2 here in this mess, and we have the integral of e to the u du, which is a simple integral to evaluate. It equals negative 1/2 e to the u plus c. We substitute u back in, negative 1/2 e to the 1 minus x squared plus c. And that is the integral of x e to the 1 minus x squared dx. Make sure I got that right. So there we go. Not too bad. Alright, so let's do something a little more tricky. So this one doesn't really follow the standard pattern you'll see for most substitution rules, which is why I chose it. So there really isn't a clear inner outer function here. So kind of have to use a different procedure for this one. So what we can do is, obviously this is in the bottom, we're not going to be able to integrate it easily, so that can be our u of x. And I'll use a different color. Set our u of x equal to 5 minus x, and our du will be negative dx. So we can rewrite our initial function right off the bat and see what happens. We have x divided by u, and if du is negative dx, then dx is negative du. We can pull the negative out to the front. So now our problem here is we still have an x, but if we look at our function of u, we could solve for x. So if we add x to both sides, subtract u from both sides, we'll get x equals 5 minus u. And if we put that in, Now we can deal with this. So we can pull this negative in and just switch the order of the terms. And now we can distribute this denominator among these terms. And we have u over u minus 5 over u, du. These u's here will cancel, leaving us with the integral of 1 minus 5 times u to the negative 1 du. And now we can easily integrate this. We'll have the integral of 1 is u minus 5, and we want to integrate u to the negative 1. Well, we just pull the power out to the front, and then we subtract 1 from the power, add a plus c. This equals u minus, actually these pluses and minuses will, these two negatives will combine to create a positive. 5 over u squared plus c. Our original u was 5 minus x. We have 5 minus x. Oh, sorry, I made a mistake. Sorry about that. Let me redo this. The integral of 1 is u, and I used the differentiation rules for powers, not the integration rule. The integral of u to the negative 1 is ln absolute value of u, plus c. So now we plug in our u. Our u equals 5 minus x. So we have 5 minus x minus 5 times ln of 5 minus x plus c. And that is our final answer. So the integral of x over 5 minus x dx equals 5 minus x minus ln 5 times ln absolute value of 5 minus x plus c. So in this case, the substitution rule wasn't really used for a function within a function. It was kind of used to get rid of this problem we had with x being in the denominator. We kind of shifted it so this more complex thing was in the numerator. You can see this 5 minus x over x turned into a u minus 5 over u, which made it easier to integrate because we could separate the denominator. So that's one case where the substitution rule is kind of different. Let's do a definite integral. So we have the definite integral from e to 1 of the square root of 1 plus ln x times ln x over x dx. So we'll go back to our procedure. Let's find an inside function. So this 1 plus ln x is within a square root. We know we can't integrate ln's within square roots with regular rules. So this is probably a good candidate for our inner function, outer function being square root. So if we set u of x equal to 1 plus ln x, and also note that the derivative of 1 plus ln x, which is 1 over x, is present on the outside. So that gives us a little more confidence about this. Du dx is 1 over x. So dx equals x du. And since this is a definite integral, we have to find the u limits. U of x equals e is ln 1 plus ln e. Ln e is simply 1. So 1 plus 1 is 2. And then we have u of x equals 1. 1 plus ln 1 is, ln 1 is 0, so 1 plus ln 1 would be 1 plus 0, which is 1. So now we can rewrite our integral with our new u limits, 2 and 1. We have the square root of u. We have ln x and over x. We have x du for dx, and these x's cancel. So now we have integral of 2 to 1 of, we can write the square root of u as u to the 1/2. This will be useful. And we have ln x du. So now we're stuck because we have an ln x. But if we look at our expression for u, kind of like in the last example, we were stuck with an x, and our u function was x, our problem, times a constant, added by the constant. So ln x, our problem, is equal to our u of x plus 1, or minus 1 in this case. So if we solve for ln x equals u minus 1. So if we put that to use, our integral is now the integral from 2 to 1 of u to the 1/2 times u minus 1 du. If we distribute this u to the 1/2, u is just u to the 1, and when you multiply the same base with exponents, you just add the exponents. So 1 is 2/2, 2/2 plus 1/2 is 3/2, and negative 1 times u to the 1/2 is just negative u to the 1/2 du. Now we integrate this, we add a power to u to the 3/2, we get u to the 5/2, and we divide by 5/2 minus u to the 3/2 divided by 3/2. And this is being evaluated from 2 to 1. And since this is a definite integral, we're not going to plug back in. This 5/2 on the bottom will become multiplication by 2/5. And this division by 3/2 will become multiplication by 2/3. And now we're ready to evaluate it. So if we plug in 2, you get 2/5 times 2 to the 5/2 minus 2/3, 2 to the 3/2, and we have all of that minus 2/5, 1 to the 5/2, minus 2/3, 1 to the 3/2. Now 1 to the 5/2 and 1 to the 3/2 are just 1. So this is just going to be 2/5 minus 2/3. And 2 to the 5/2 is, we can't really do anything with it because the square root of 2 is not a natural number. So we can look at these 2's out here as 2 to the 1 and just add the exponents. So we can have 2 to the 7/2 over 5 minus 2 to the 5/2 over 3. And if you want, we can distribute this negative. And there's not much more simplification that can be done here. And that is example 3.